So in this last bit of programming 2, we're going to start learning about data structures and programming. And in particular, we're going to be looking at linked lists here very soon. But in order to understand linked lists, we need to understand what's going on in memory and how our computer stores information a little bit more carefully than we have so far. So I've set up a virtual memory here. So you can think of this as being like a memory chip in your computer. You're going to store information in it. Each one of these cells is a place in memory. And each one of these cells we think of as storing a byte, 8 bits. And if you remember our ASCII tables that we looked at last semester, with 8 bits we can store all of these letters and punctuation symbols. These are addresses. So each piece of memory has an address, a physical address. And so I've addressed this 0 to 32. Now here are 2 strings. So I've been playing around my word processor and I've typed in 2 strings. Actually this ends in a period and so does this. And those I want to enter into memory. So I have the I don't like Sally here. That occupies spaces 0 through 18, and hello, which occupies spaces 19 through 24. Alright, now a couple of things are going to happen. First of all, I'm going to edit this phrase, I don't like Sally. Seems a bit negative. And then I'm going to add in Jim's place. So I want to look at how that happens. Now, what I want to do is go from I don't like Sally to I do like Sally. Be a little friendlier to Sally. Which means that I need to get rid of these 3 characters in memory. Now, when we do that, we've freed up 3 pieces of memory here. But the question is, how do we handle the rest of this? Because now the phrase I do like Sally is disjointed, or as we say, fragmented. And it's fragmented in this part, this I do, and then the space I like, or like Sally. So what we could do is take all of this, the like Sally, and push it up and reclaim this lost space. But if we do that, it takes time. If this is a particularly long phrase, or it could be a picture we edited and we took a few pixels out or something, we have to move that entire picture. That's a lot of work and very inefficient. So in fact, what we're going to do is leave I do like Sally right where it is, and we're going to keep track of. So your computer keeps track of this for you. It keeps track in a table that says that this phrase is stored in 0 through 3. So the cells 0 through 3 and 7 through 18. The 7's for the space. So there's a space right here. And then these are just empty. Now, technically, I've actually done something wrong. I shouldn't have erased these, because when you erase the don't, the N apostrophe T, and I don't like Sally, all that really happens is this table information gets updated. These cells actually do have the N apostrophe T still in them, but the reference to what's being stored has changed. This is why we initialize our variables, because when you initialize a variable, that variable gets stored or assigned to some place in memory and you don't know what's in there. Could be some dilly-dallying about N apostrophe T. Okay, but now I'm going to go back and erase these again, since we can pretend like we know what we're doing. And I want to add in Jim's place. So the way Jim's place is going to work, now over here I don't have room for Jim's place. This is 11 characters and there's not enough slots here, but if I make use of these available slots, let's see, Jim's. When you type in an apostrophe in Excel, you have to use 2 of them to get it to show up. It's kind of annoying. But with that freed up memory, I now have room for Jim's place. And Jim's place is now in 4 through 6 and 25 through 32. Okay, so what should you take out of this video? You should take out that, one, we can store bytes, characters. Should have already known that, actually. that they are stored in memory, and memory is addressed. And when you store some kind of string or paragraph or picture, anything that's a conglomeration of information that belongs together, there's actually a table out there of the various places in memory where that thing is stored. And they're all comprised of addresses, so each place in memory has an address. Alright, now we're going to use this to start building up our linked lists. Okay, so now that we've seen a little bit about memory addressing, we can start talking about linked lists. And I'm going to use the string Jim's place to illustrate the idea of a linked list, but I want to be clear that we don't have to use a bunch of characters. A linked list can be built up from anything. It can be letters, it can be strings, it can be numbers, it can be pictures. Any object you can store on a computer can be stored in a linked list. So hopefully I can convey that general idea as we move along. So here's the idea. I have a bunch of things that I want to store, and they're related to each other. In this case, I want to store the letters J, I, M, apostrophe, S, P, L, A, C, and E. But again, these could be pictures, they could be data structures, they could be classes, whatever. And I want these things to be organized together. So one way to do this is to have a start or head of this thing. So when you assign a variable, so let's pretend that we had Jim's place somewhere in our code. We had something like x equals Jim's place. Okay. Then what really happens here is Python figures out that you want a string. It puts that thing in memory, and it gives a value to x of 4. So x is really just what we call a pointer. A pointer is an address. X is really a pointer in the memory saying, hey, I got a string stored here. And it's actually, x has more to it than that. It stores some information about the fact that this is a string. But for now, we're just going to think of this x equals as assigning a pointer to the variable x. So if you have a linked list, first of all, you need a head. You need a start of where your linked list starts. And our linked list starts, in this case, with Jim, which is at address 4. Now, the next thing, and I'm going to talk first about singly linked lists. So the next thing in our singly linked list is an I, which is address 5. So where I'm storing this J, I'm going to put a 5 with it in the next spot, which tells me that the next item is at position 5 in memory. Now, I should point out that in Python, this is not a natural thing to do. You have to kind of force the issue here to talk about linked lists because Python does not have pointers the way that some other languages do. In the C programming language, for example, you can define a pointer, which is literally an address to where that variable resides in memory. And again, a variable can be anything, string, class, picture, whatever. But in Python, well, we're going to have to work a little bit to make linked lists work, but we can make it happen. Okay, so now J is linked to I, and then I, the next thing after I is in position 6, that's the M. The next thing after the M is the apostrophe, which is at 25. So we'll get a 25 here, and then it goes 26, 27, 28, 29, 30, 31, and that's it. The E doesn't have anything after it, so we leave that blank. This is what's known as a singly linked list, and apparently these two things fell off the radar somehow. Okay, this is what's known as a singly linked list, which means that each thing in the list has a link to the next thing in the list. So here's how we would picture this. So we picture singly linked lists as a box. This has the information in it, so this might have the J, the I, the M, the apostrophe, and there's more obviously in the example we're using with Jim's place, more boxes, but I chose to draw this many. And then for each box, there's an arrow pointing to the next thing in the list. So this is what's called a singly linked list. And then you have something that's pointing to the beginning so you know where the beginning is. Now there's an obvious problem with this. If you want the thing in this position, you have to go to the beginning and chain your way through to get to the thing in that position. And if you happen to be at the end of this thing, it doesn't matter. If you want the thing in the third spot and you're at the fourth spot, you can't go backwards. You have to go all the way to the beginning and then link your way through to get to the third spot, which might seem a bit crazy. Actually, when the modern view of that is perhaps it is a bit crazy. But you have to remember, in the early days of computing, memory was something that was very, very precious, very expensive, hard to come by, and there wasn't a lot of it. So if you could conserve memory, you did. And every time we store a pointer to something, that takes up memory. In fact, a fair amount of it. So singly linked lists were more useful, perhaps, when memory was a little more dear. Now that memory is pretty cheap, we use something called doubly linked lists. And in a doubly linked list, basically you just have arrows going both ways. So if I am at this point, at this piece of memory, whatever this object may be, I can go backwards to the one before it. So you can traverse the list in either direction, doubly linked. In our Excel example, that would mean that, well, let's see, J is at the beginning of the list, so there's nothing to link to back here, but I would point back to the J, the 4. The M would point back to the I, which is 5. The apostrophe would point back to the M, which is 6. The S would point back to the apostrophe, which is 25, and then this goes from here. And the last thing in the list this time gets something in one of its links. So we think of these as 3 different spots. And the thing that's a little bit deceiving here is that I've drawn these boxes as the same size, but that's not quite what's going on here. This is some kind of object that we're storing. This is a pointer, and this is a pointer. These two things would have the same size, their address, but this thing could be huge, could be tiny, who knows? It's whatever we're storing. But here's the idea. So if I happen to be at position where the A is, and I want to back up to the S, I say, well, go to 28. 28 takes me to... Uh-oh. Did I goof this up? Let's see. A should take me back to the L, which is 29. Oh, I numbered somehow wrong. What did I do? Let's see. The S goes back to the apostrophe. Oh, I missed a space. There's no space in here. Easily fixed. So this has been wrong the whole time. I wonder if any of you picked up on this. I'm the only dope that didn't. Huh, problem solved. Okay, so now it works. Does it? Let's see. Yeah. Okay, so where was I? Suppose that I am in a space where there's an A, and I want to back up to the capital P. So I go to cell 28, which is the L. I look at the L. Still not a capital P, so I back up to the space that's at address 27. And lo and behold, I find the P and say, got it. So you can go forward in any direction. Suppose I was looking for the A or the C that comes after this. So I go to the next cell, which is 28, which is an L. And that's not a C. I go to the 29 cell, which is an A. That's not a C. Go to the 30 cell. That's a C. Found it. So with a doubly linked list, you can search forward and backwards. All right. Now, my next trick is going to be to show you how you can put these things and implement them in Python. Sort of.